All right. Thank you, Aaron, and thank you all for being here. This is a very exciting and very strange topic to go into when we're talking about general relativity. So let's ease into it pretty nicely. And by that, I want to actually start with a couple of things. First and foremost, we're talking about relativity. Just to be clear, we're not talking about moral relativism. That's a very different subject. So some people sometimes conflate those. It's worth actually noting. Yes, when we're talking about relativity, we can say that proper use of relativity may result in properly functioning GPS systems, properly accounting for interplanetary communication times, the detecting of gravitational waves, building foundations for a variety of possible cosmological models, the detection of exoplanets, measuring fundamental properties of the universe, and seeing stars located behind the sun. Side effects may include forward time travel, dimensional contractions or expansions, relativistic beaming, gravitational redshift, resolvable twin paradoxes, apparent superluminal velocities, hyperdimensional thinking, and the collision of stars or stellar remnants, and in some cases, spaghettification. Ask your local scientist if relativity is right for you. So this is a very deep and interesting subject, but if we really want to get into it, we want to actually take a step back to a little bit over 100 years ago. We actually want to see where this all came from, but before we do that, let's see how things actually work in the everyday. When we're looking around, we don't really notice the effects of general and special relativity in our everyday lives. This is a very very obvious reason for this. Well, we can see through an example. Say, for example, we have two cars driving down the road. One moves twice as fast as the other. This is a nice, simple thing. You could actually say, okay, if you're in that slower vehicle, you could say, well, clearly that car is going as much faster than me than I am going. This is a interesting, nice, simple, mathematically way we can actually describe how things are moving, except that's not exactly how everything works. It really depends on how fast they're actually going. At normal, everyday speeds, you could actually say that the difference between those two velocities is equivalent to the velocity of the slower car. But if you were actually looking at something moving at near the speed of light, things get weird. And because we don't really easily perceive these effects, we really didn't know about relativity until the early 1900s, when we actually had this dawn of modern physics, when physics took an interesting turn. So now let's go ahead and take a step back and look at that. So when we're looking back here, this is James Clerk Maxwell, and in the 1860s, he did something phenomenal. He was actually the one who figured out that light was an electromagnetic wave. And for those who are the romantic type, there's a legend that he, after first figuring out that that light is an electromagnetic wave, he took his fiancée out and looked up at the stars and said, "What if I told you I was the only person in the world who knew what it was that was going into your eyes?" Aww. Yep. He was trying to swoon her quite as well. But nevertheless, he determined this very, very important thing, and one thing that was very critical of this was that he found that the speed of light should be a physical constant, because he actually derived it from other physical constants. All right, shortly thereafter, Michelson and Morley were able to actually very, very accurately measure the speed of light, and very importantly, determine that light did not need a medium to travel through. They were looking for the ether, and they actually were unable to find it. Now, Michelson had some interesting thoughts, which we will note here. Now, in 1894, he actually commented on the state of science at the time, and this is a really big quote, but there's a few important notes in it. He notes in particular that it seems probable that most of the grand underlying principles have been firmly established, and that further advances are to be sought chiefly in rigorous application of these principles. And by that, you can see later on, he basically is saying that an eminent physicist remarked that the future truths of physical science are to be looked for in the 6th place of decimals. He was saying, in other words, that we basically figured out the universe, and now all that's left is to get very, very precise measurements and go from there. Now, you'll also note he did leave a caveat, a very important caveat, because as it turns out, this was really a within about a decade of some dramatic turning points in physics. This is where classical physics reached its peak and what is termed modern physics first actually arrived. Again, 10 years later or so, in the early 1900s, we had Max Planck and Albert Einstein. They produced some evidence to suggest that light exists in packets of energy, which are termed today as photons. This is a term that you've likely heard before because they're postulating and arguing was actually fundamentally important, and that's actually one of the things that Albert Einstein got his Nobel Prize for. He did not actually get it for what we will spend all our time talking about today. He did not actually get a Nobel Prize for anything having to do with relativity. Now, that all actually came about in between 1907 and 1915 is when he published those papers on relativity, and the actual details for relativity really do hinge on two very specific postulates, two specific ideas, one of which we've already touched on. It's the second one, but the first one is the principle of relativity. And what he actually is postulating here is that simply the laws of physics will be the same no matter what inertial reference frame you're in. And inertial in this case just meaning non-accelerated, just out there in space, two specific points of reference are identical. And what that ends up having a very important effect because of the second postulate, the constancy of the speed of light in a vacuum. In other words, the speed of the light in the vacuum will have the same value in all inertial frames of reference. And that speed is around 3 × 10⁸ meters per second, so that's 3 with 8 zeros behind it. It's very fast, but the actual speed is really inconsequential to our talk to some extent. So we are really noting these two things really drive the outpouring of everything we're about to talk about. So everything's the same. Physics works the same in all inertial reference frames, and the speed of light is basically a physical constant, as Maxwell really derived. And so what actually comes out of that is some interesting stuff. So if we're looking at two different reference frames, one stationary, the unprimed black reference frame there, and the one moving at a velocity v, the primed one there, we want to actually describe how one goes from one to the other. And the way you do that is through a Lorentz Transformation. And math! Don't worry, we're not actually going to go into much of what this is actually saying. The real thing here is that the important thing we're trying to say here is that in order to transition one's perspective from a non-moving frame to another, you actually have to deal with the fact that time and space are actually both intertwined. You have t for time and x for space, likewise here. So you have to deal with both of those together to switch reference frames. That's a very important thing. So don't worry about the rest of that equation that literally only has one number in it. So yes. All right. So really, if we want to address those subjects, we have to take a step back. We have to look back and try and define what time is. And really, what it comes down to, or rather one way of describing it, is to simply say, well, time is what you measure with a clock. This is a very strange way of actually defining time, and in fact, it should feel rather unsatisfying, because we're just saying, well, it's a clock, that's a measurement device for this thing. That's not the way you should be defining it. It should grade against you for this particular definition, but nevertheless, this is a worthwhile way for us to actually describe how time works, because we will need to actually look at clocks in order to actually figure out how to look at time from different perspectives. And so whether in our minds, our wrists, or hanging on a wall, it's still worthwhile to actually talk about time with some kind of measurement device in mind. Okay, so how can we actually do that? One great way is with a photon clock. These don't actually exist, but they're great and easy to talk about in theory. So basically, if you had a stationary clock, what it is you have two mirrors. You have the blue objects are your mirror, and this little ball is the actual photon that we're trapping in between them. It literally bounces back and forth very rapidly between those mirrors, and it will take a given amount of time to travel between one mirror to another. That is what a photon clock is. It's a way of saying, okay, one tick is it going up to the top, it bounces back down, that's your talk, and so there you go, tick-tock, away it goes. But what we see, interestingly enough, is if this photon is actually, or this clock is actually moving. That is, the photon trapped in there is moving with the clock, and as such, if the clock is moving to the right, it will, by the time it reaches the top, it will have moved that far, and it will go up at an angle and bounce off there. Now, the important thing to see here, and what should be readily obvious, is that those two lines, the arrows in between the bottom surface and the top, are not the same length. Now think back to what Einstein's postulates say. The laws of physics are the same in all inertial reference frames. A moving object is in a moving inertial reference frame. So, okay, physics works the same in both these places. But what we're also stuck with is that the speed of light is the same in all inertial reference frames. So if it takes 1 second for this thing to reach the top here, for the person moving with that clock, that same photon should take 1 second to reach the top. But clearly it's going a longer distance, so the speed of light is invariant, meaning us looking at it from an outside viewpoint should be seeing the same amount of time for it to travel up, but it's going a further distance. In fact, what we actually do see is that it does take longer for that photon to reach the top if we're watching a moving clock. But if you're moving with that clock, that same time frame for them, it's as if it's stationary, so they will see it move up in 1 second. These are two clocks that don't agree with each other, is what we're coming down to. And that is an important notion called time dilation. What we're saying is that if you're stationary with your clock, you're going to measure it, but if you're moving with respect to that clock, you'll actually see a change in the way time passes in that clock itself. This is where things start to get really weird, but we have to take another step to actually really understand what's going on here, and that is, like, ask another question like, what is length? You might expect the answer, it's that which you measure with a ruler. Again, this is not a satisfying definition, but we can definitely learn from it. So like what we saw with time, we can actually extrapolate to see what happens with length. If between two reference frames, time and space are linked, and if time experiences some changes when comparing two reference frames, what we actually see then is a very interesting thing called length contraction. Yes, what we actually are saying is that when one frame moves with respect to another, a given ruler, if you had a ruler and it was moving very fast with respect to you, it would actually shorten. Which, does that mean that it is actually, its space is actually shorter? Like if you were in that space, would it feel more cramped? Well, no, because you would also have been contracted as well. This is saying that if you are in that frame of reference, everything feels fine, but if you are watching that frame of reference moving, everything seems contracted. This is all very weird, and it should seem that way. Okay, length is an interesting thing. Let's actually take a look at that another way. Say you're measuring a stationary object, it ends up looking like this. If we were looking at a moving object, say it's moving rapidly that way. Oh, I've got water. Yeah. If it's actually moving rapidly that way, what we would actually end up seeing is something squished like this. That would be the same triangle, but if it was moving, it could actually be compressed. This is not something you notice every day because big objects don't tend to be moving at near the speed of light. This is what you would see, or what you would actually measure, rather, if you were looking at an object that was moving at a significant fraction of the speed of light. Okay, so that's what length contraction means. But, okay, so we've talked about time and distance. Well, those two things normally go into actually tell us one particular thing, and that is speed. So again, time and length are both relative measurements. So what can we actually look at with regards to speed? Well, we've talked about looking at things from a stationary perspective or a moving perspective. The big question is there a universally accepted stationary point? Nope. No, there is in fact no universal stationary point anywhere. If we look at the Earth is rotating, so it's not clearly on the Earth. Could it be the center of the Earth? No, the Earth is revolving around the sun, so it can't be on or in the Earth at all. What about the sun? No, the sun is actually orbiting around the Milky Way galaxies, so it can't really be seen as a stationary reference point. What about the galaxy itself? Is it actually stationary? Well, the entire thing's rotating in an interesting way, and we can actually measure what's called its peculiar motion, its actual motion with respect to the galaxies around it. This is all a way of saying we have no stationary point with which to measure speed absolutely. So this is where it gets especially weird. If we have no specific point of actually referencing stationary and moving, then we actually have to look at things moving from multiple perspectives. So we're going to talk about a nice little example of two ships passing in the night. Say we have two identical spacecraft. One is quote-unquote stationary as we're looking at it. This is Aaron's spaceship. The other is moving at a significant fraction of the speed of light. That will be Bob's spaceship. And what you actually see when these things pass, notice carefully because Bob's ship will be length contracted. Watch the sequence of events that happens here. The tails line up first, then the noses do. Again, we'll do that one more time for the sake of seeing that. The tails of the spacecraft line up, then the noses line up. This is the order of events as Aaron sees them. This is an important thing. But if we actually look at things from another perspective, again, there is no absolute reference or stationary point. Then if you're with Bob on his spacecraft, everything looks normal. Everything is normal length. And in fact, instead of seeing him as flying past Aaron you could actually think of as moving backwards with respect to him. So all of the principles that we've been talking about already apply to Aaron, so he's actually length contracted as well. And so when he flies past, the noses line up first, then the tails do. Again, that should seem weird. The noses line up first, then the tails do. This is, in fact, the opposite of what we just saw from Aaron's perspective. They are literally seeing opposite perspectives. So who's right? They both are. This is, again, very strange that we would actually be thinking of that. But the way we actually address that is we must actually change the way we think about time. This is one thing we were referencing with that photon clock. This is another way of looking at that. So when Aaron's looking at Bob's ship, he will see one perspective, but Bob will see another. And the way you actually resolve that contradiction is when you're actually looking at the spacecraft. The clock that you would say have at the tail of Bob's spacecraft, when you're looking at Bob's spacecraft from Aaron's perspective, will read out a different number than the one at the nose. So literally, as Bob is flying by, Aaron is seeing different parts of the spacecraft at different times. He's literally seeing two different times at one time, and that's how he can actually see a different sequence of events. Again, this should be weird. This should not make intuitive sense because that's not what we experience every day. We should, when one car passes by another, everyone agrees that the front of the cars align at the same time as the back ends of the cars, or if they're at different lengths, they at least agree on the order in which it happens. But if things are going fast enough, things get weird. And you have to actually consider that time is not a uniform thing that is applicable to all reference frames, and in fact can be different across one object when it's moving at a substantial velocity with respect to you. This is weird. So it gets weirder. Because what we've talked about thus far is how things actually are measured, what is actually going on. This is not the same thing as what you would actually perceive as something goes by, because light actually has to travel to your eyes, and that's an important distinction from what you're actually looking at, or from what's actually going on. What that ends up looking like is a bit like this. Let's see, that should restart. There we go. So your measured contraction is what's on the left. That's what we've been talking about. But when you actually take into account light traveling to your eyes, things have a tendency to appear to even rotate weirdly as they compress in length. And you get a very strange appearance of an object. Okay, so that's another weird thing going on. Well, have we actually seen anything like this going on? Well, yes, if we're actually looking out into the universe, we can look at these things called radio galaxies, or what they are actually driven by are active galactic nuclei. They are essentially, matter is falling into the black hole at the center of these galaxies. They are supermassive galaxies, and when matter falls in, black holes have a tendency to not eat everything. They have a tendency to actually accelerate and spew things out along the poles. And this is a really interesting place to see relativity on a large scale. And when I say large, I mean large on even an astronomical scale. So what these actually end up looking like would be something like this. This is what you would expect to see at the center of an active galaxy. It is a quasar. There's an accretion disk, this big mass of gas and dust falling in, and you'll see way up at the top this jet shooting out. And that jet shoots out at incredible speeds, so much so that if you actually viewed it from a certain perspective, you might see something very strange. You might measure the speed of that and actually see it as going as if it's faster than the speed of light. That should really come across as an interesting thing, because when we actually look at things, nothing should actually travel faster than the speed of light. So why would we actually see something showing up as faster than the speed of light? Well, the reason for that comes from that perception versus what is. Now, let's see. Should go on to this one. So this is another perspective on such things. Those jets move at such a high rate that on a large scale, if you're looking at the entirety of a galaxy, you could see plumes coming out of either end of it on a massive scale. This one looks out at hundreds of thousands of light years from end to end, which is a huge scale for these jets. And the reason you see it that way is because of the speed they're going. But again, this should be confusing because we're saying that they're going faster than the speed of light. That doesn't make sense. This particular galaxy is one of the brightest radio objects in the Hercules constellation. It is, in fact, the brightest and one of the brightest in the entire night sky. What you're actually seeing out at the ends are those same jets going out at a distance of 11 million light years across. So that is much bigger than the distance between us and Andromeda, the Andromeda galaxy, that is. This is about as big, or it's near the size of the whole local group of galaxies. What is going on? How are we actually getting such immense speeds? Well, it all comes down to perspective and perception. That light actually has to travel to you. So if you're looking at something that's coming towards you and it's emitting light that's only going, say, 10% faster than the object itself, you will get that information all at once. And as such, it appears to be going faster. It appears to be going 10 times the speed of light even, because it traveled at such a rate that it's trying to keep up with the light itself. You'll notice the same kind of delay if you're ever out on the water, say, talking to someone on a boat that's quite a ways away. You might actually hear them from a different place. Or if you watch aircraft flying overhead, you might actually notice the sound doesn't correspond to where the actual object is. It's because it takes sound time to get to you. Likewise, when light does that, it makes it look like things could be traveling substantially faster if it's going directly towards you. So that's the real solution for that. And this particular object is an example of some really crazy huge and high energy physics that's going on that relativity really helps us actually understand. Okay, so we've talked about speed and length and time, but what about acceleration? This is another interesting thing because, again, everything we've talked about so far is with constant velocities in that inertial frame category. Now, when we're actually talking about our everyday experiences, we feel acceleration, not motion. This is an important detail because if, say, we actually blacked out these windows and tried to figure out what's going on, we would not necessarily be able to tell the difference between being in here on the surface of the Earth or being accelerated up at the rate of the acceleration due to gravity, 9.81 meters per second squared. If we're going up at the same, accelerating upwards at the same rate as the acceleration due to gravity, this room, we would have no idea that we were off the Earth if we were actually moving like that. Here's a nice little cartoon example to actually be able to discuss that in a way that makes graphical sense. The room on the left is actually accelerating upward, while the one on the right is actually in a gravitational field, and the ball is tossed and ends up having the same motion in those two rooms. So you'll see the one on the left, there's no gravitational field, so the ball just travels straight upward, but there's gravitation on the one on the right, and that actually has that same arcing pattern. They move the same way in the two rooms, but the entire physical process is incredibly different. This is a weird thing that actually is very important, though, because if we want to talk about how gravity works, if we want to generalize the way we talk about relativity, we can actually do that by treating gravity like acceleration. This is where that term general relativity comes from. What we've talked about before is that special case of relativity, the special scenario where we have no gravity acting on your inertial reference frame. We have nothing going on with it, and so we can actually do all sorts of different things and compare frames nicely. But this is where we actually get a general term that we can apply to a lot of real physical instances throughout the universe. But with generalization comes even more weirdness. So it's going to get even stranger here. So we're looking at the actual distortions from gravity, and if we distort space in special relativity, if we actually compress it in certain ways and we have time operating a different way, in order to get that to work in a general sense, we actually talk about the curvature of space. Now, imagining this in 3 dimensions is quite difficult because you're actually thinking beyond 3 dimensions of space, but we can actually start in 2 dimensions, sort of. The sort of aspect comes from the way you actually see these grids of stretched space. They are, in essence, 2-dimensional in and of themselves, but if we actually look at it, you need 3 dimensions to actually describe it, because you're taking that 2-dimensional flat surface and bending it into a 3rd dimension. So if we're going to talk about general relativity, we're talking about a 3-dimensional flat surface bent around a 4th spatial dimension. Yes, you did hear me right. In order to actually talk about this or in order to actually have general relativity work, we have to think about our 3-dimensional space being bent or curved in a 4th spatial dimension. I'm not talking about time as the 4th dimension. No, that's separate. We're talking about an unseen, really interactable 4th dimension about which we bend the entirety of 3-dimensional space. This is that side effect about hyperdimensional thinking. But if we're actually looking at how things would move on this 2-dimensional surface that we can understand, we can actually see that if it passes close to the Earth in this picture, it will actually deviate from a straight line path if it's just trying to move in a straight line. We're not talking about it necessarily being, gravity pulling it down towards the sheet. No, we're just saying that the path of any object rolling near the Earth will curve a bit just to go along the shortest distance, because the shortest distance between 2 points is not always a straight line when you actually have the space itself actually bent in a certain way. And this, again, is actually how we get to gravity. This is the way you actually have acceleration talked about and mapped onto space, and that's how we actually can talk about this as being the way gravity works. We're saying that mass actually causes a distortion of space-time itself. But what I mentioned here was an object moving past the Earth, but there's no reason for that object to have any mass. So if we actually look at light passing through these things, we can also expect it to be bent and moved about by gravity. And this is an effect called gravitational lensing. It's a very important effect that we actually observe very often in the universe. The way this actually looks is, say you have a very distant star or quasar like this, and the light is actually passing around a nearby galaxy. It's behind it in a very specific configuration, and the light rays are bent back so they converge back to the Earth. you can see some interesting images. And in fact, there's an example of what's called an Einstein cross. It's 4 different images of that quasar splayed out around the galaxy itself. We've actually seen these, and we've verified that's the way things are actually working, because we can see time-based patterns actually show up in a specific order across those different images. Okay, so that's nice and useful. It's very interesting and weird, but let's look at it another way. Here is a massive set of galaxies, and what we're looking at here is a variety of images. Those 4 circled objects around there are all actually the same object, actually being projected around this very massive object in the center. These 3 things here are actually a galaxy behind all of this that's showing up in 3 different places because of that same gravitational lensing effect. And just for reference, there's also a supernova highlighted there that's useful for actually figuring out distances to those objects. Okay, so that's a nice, interesting, strange, weird thing, but we see it also in other places. This is the Cheshire Cat galaxy group. It is, yes, very much so face-like, but in fact you can actually see very spread out and distorted galaxies there, one down here and another one going all the way up on the side here. They're all being lensed by these 2 very, very massive galaxies right in the center. Those massive galaxies are actually in the process of colliding. This image is actually utilizing both optical and X-ray data. The violet is that X-ray data, and X-rays are emitted from very, very hot gases, and so these colliding things are actually producing a lot of X-ray light because they're colliding in that way. So, okay, gravitational lensing is really interesting and weird, but what else is even going on there? Well, we can look on a much, much, much larger scale and look at the entire universe itself, because we can actually ask the question of what is the shape of the universe? Is it like what we saw before, the 2-dimensional grid? Is it flat? Is it an open universe? That is, does it go on forever, or is it closed? Is there an end? Well, how can we actually describe what the entire shape of the universe would actually be? Well, we can look at the Earth as an example of a closed space. So take that grid that you saw before and wrap it into a sphere. That is an idea of a closed space, because if you actually go far enough on the Earth, you eventually come back to where you were. There is a finite limit on space. Again, that would be your 2-dimensional space, the surface of the Earth, bent around a 3rd dimension to make a sphere. That is what we're talking about. So if the universe was closed, we would expect it to sort of be a hypersphere, a 4-dimensional sphere, or some similar type of shape. When we've looked around and looked at very specific things to try and measure curvature of space-time itself on the largest of scales, we've found everything seems to indicate that it's right around 0. So we're looking at probably a flat universe, one that is not bent in any dramatic way. And it also appears to be open, which means we actually are looking at a literal, potentially infinite universe. Now, there will always be some question as to whether or not the universe is slightly curved in one way or another, but that's because measurements can only be so precise. We'll go right back to Michelson and his comment about the ever-increasing precision of measurements, but that is a very important detail. Fortunately, we do still expect lots of really interesting science. So, moving forward, though, into that interesting science, we can also talk about something called gravitational waves. This is really interesting and a brand new field, really, in astronomy. So say you had 2 massive objects that were orbiting around each other very close together, like not just the sun, no. We want to get something more dense and closer together. Typically, you talk about either 2 white dwarfs or 2 neutron stars, the dense cores of dead stars, or rather the dense remnants of dead stars, and you put them very close to each other, and you can actually see those distortions actually propagating at the speed of light. If those 2 objects orbit in a short enough time frame, the actual time it takes for the distortions in gravity to propagate, to reach the other star, weird things can happen, and it can actually cause their orbits to decay and drive them to collide with each other. And what's interesting is if those distortions are big enough, they will actually emit waves out into the universe, and it's not a matter of they may be detectable, it's a matter of we have found them. So this is a little interesting, just 5-minute thing on that actual first discovery of
Gravitational waves were predicted by Einstein almost 100 years ago.
Well, a gravitational wave is a ripple in the fabric of space and time. It's produced somewhere in the distant universe and travels across the universe.
When any massive object moves, it's changing the nature of space-time. That's what Einstein told us.
So you have a motion that stretches space in one direction and compresses space in the other direction.
Nobody really believed at the time of the prediction that you could ever detect them because the size of the effect is so small.
It was what we call a chirp, and it was strong.
Everybody thought it was a fluke, it was too good.
And I thought, my God, this looks like it's it.
Oh my gosh, this is real. It took us 25 years and 2 detectors to finally detect a gravitational wave. We have interferometers, one in Hanford, Washington, one in Livingston, Louisiana, to detect the stretching and compressing of space.
We literally look for changes in the space-time distance in our instruments as the gravitational wave goes by.
And the gravitational wave pushes them together and apart by 1/1000th the diameter of the nucleus of an atom. No wonder it's taken so long to pull this off.
However, what's even more remarkable about this is what we detected.
We have observed gravitational waves from 2 black holes forming a larger black hole.
For the first time, 2 black holes
Spiraling together, coalescing, merging, creating wild oscillations. A storm in the fabric of space and time.
They're moving at the velocity of light, damn near that velocity. 30 solar masses moving that fast. I mean, they're putting out incredible amounts of energy.
And when they collide with one another, they produce a bigger black hole, but they also produce gravitational waves. And in that process, about 3 solar masses just disappears and goes into gravitational waves.
Oh, it's going to be amazing. We have always said that this is going to be a field called gravitational wave astronomy.
Gravitational waves carry information that you can't get from any other way. A supernova, 2 neutron stars colliding, even the Big Bang itself, the beginning of the universe, all produce gravitational waves.
This first detection by LIGO is the very first step. It's just the start of the story nature is about to tell us.
I would love to see Einstein's face. I mean, he would have been as dumbfounded as we are, because it's a wonderful proof that all of this incredible stuff, the strong field gravity, is in his equations. Just imagine that. To me, that's a miracle. It settles the question for astrophysicists. Do black hole pairs form? Yep, we got one.
So this is a very interesting new development. This particular detection came back in late 2015 and on into 2016. 2015 was the original discovery. 2016 was when they actually announced their second discovery as well. I was fortunate enough to actually be at the conference that they announced their second black hole merger. But this is not the only thing that they've actually been able to discover with the LIGO Observatory. They've actually also found merging neutron stars. Now, this is a very interesting thing. What a neutron star is again, it's the remnant of a high mass star. When a star that's bigger than around 8 to 10 times the mass of the sun reaches the end of its life, it actually explodes in a supernova and will leave either a neutron star or a black hole, depending on how massive it is. Now, the neutron stars we've found can be in pairs, and we've found them elsewhere, but we actually found a point where they actually collided together through that same process I mentioned, where they actually lose track of each other, basically, in the propagation of the effects of gravity, and they come together and collide. And what that actually ended up looking like, well, this is a nice dramatic version of that. You actually had a bit of the gravitational waves being emitted, and they spun up really rapidly together, and then gave a nice explosion. That explosion was incredibly important because this particular detection was viewed not only with gravitational waves, but it was followed up with gamma rays, with X-rays, with radio waves, and with optical telescopes. This was one of the first very transient objects observed with much of the entire electromagnetic spectrum, but it was also observed with gravitational waves, and that was one of the first things that actually detected it. This is a crucial thing because of what it actually represents, because we are often trying to figure out where all of stuff comes from. That is nucleosynthesis, the synthesis of the elements. And if we actually look at this detection, it is important because if you're looking at all of the yellow stuff on that periodic table, that is what we expect to come out of the merging of neutron stars. That particular explosion was a nuclear furnace producing many of those elements there, including silver and gold all come out of that, a variety of other ones. I could go through the list. There's plenty of things in there. Uranium and even plutonium is also predicted to be formed in that same mode. This is crucial evidence for us to actually figure out how the universe is working. And if we did not have a gravitational wave observatory looking for this particular thing, we may not have known what it was. But two neutron stars colliding produces a very unique signature relative to two black holes colliding. And so they were able to say this was neutron stars. And when they followed it up with observations, we were able to get a lot of really worthwhile information. So this is really the start of an entire new branch of astronomy. And again, when I say that, I'm talking from the very beginning of time. We've really only done astronomy using electromagnetic waves, using that very thing we started with, which James Clerk Maxwell described as electromagnetic waves, which we now think of also as being packets, wave packets of energy, photons. All of that was how we do astronomy until now. Using those explorations of light to actually go into talk about relativity and everything has allowed us a new way to actually see the universe itself by using gravity as a fundamental actual way to view into the heavens. It's a wonderful new thing, and I'm excited to see where everything's going. This is all brand new. Within the past couple years, this has really come of age, and we are just beginning to find a new way to step into the universe. So thank you, and I look forward to seeing where everything goes.